Okay, first of all, I would like to thank the organizers for having me here, and thank you all for coming so early, at 9, not 9:15. Okay, so since most of the people here don't care probably about non-commutative geometry, I should probably start by explaining why anybody would look for any kind of Hodge structures in non-commutative geometry. So I should start with some piece of motivation. So motivation comes from mirror symmetry. Needless to say, I will not give any decent overview of the history of mirror symmetry, but I just want to mention some results from the past that are relevant for my talk. So the story goes to the 80s and the early 90s. So that's when physicists discovered this mirror symmetry phenomenon. So to any Calabi-Yau threefold, they are able to associate two topological string models. They call them A model and B model. And so Calabi-Yau threefolds, according to physicists, should come in pairs. So that the A model of M is isomorphic in some sense to the B model of W and vice versa. And of course, these claims don't make much sense since we don't know what these A model and B model are, but they were able to generate an exciting mathematical prediction. So the number of curves of genus 0 rational curves in M can be calculated in terms of periods of W. Okay, so everybody knows this story, but then a bit later, Kontsevich proposed his homological version of the mirror symmetry phenomenon, which he believed would provide a conceptual, that's his own words, conceptual framework for possible explanation of this prediction. So this homological mirror symmetry states that something called derived Fukaya category of M should be equivalent to the bounded derived category of coherent sheaves on W. Okay, so we can take this literally and ask ourselves, can we really extract, so suppose we can prove this equivalence, can we really extract the original claim from this equivalence? Well, to begin with, maybe I should say that a bit later, physicists identify these two categories as the categories of boundary conditions in the A model and the B model, respectively. So somehow this equivalence is consistent with what comes out of the study of topological string models. And some physicists, if I understand correctly, they share this expectation that open strings are more fundamental than the closed ones. But anyway, so suppose we want to derive the original conjecture from this equivalence. So it's not that easy unless we are able to reformulate the original claim as some kind of equivalence between data of the same type. So these a number of curves and periods, they look completely different. So let me write here. So in the late Baranikov and Kontsevich kind of upgraded this original conjecture to a statement about an isomorphism of two so-called Frobenius manifolds. Okay, so this Frobenius manifold had been known, but what they did, they introduced some Frobenius manifold on the B side of the mirror symmetry. And for that purpose, they developed what they coined the semi-infinite Hodge theory of Calabi-Yau manifolds. And actually, mirror symmetry, this was already in any dimension. Well, but actually, first examples of semi-infinite Hodge structures appeared much earlier, maybe in the late 70s, I'm not sure, in the work of Kyoji-Saito in singularity theory. And he essentially used them for the same purpose, for constructing some first examples of Frobenius manifolds. But neither the term semi-infinite Hodge structure nor the term Frobenius manifold existed at that time. So it was some kind of version of Saito's theory of primitive forms in this setting. Okay, but what is remarkable about this is that Baranikov and Kontsevich were already inspired by homological mirror symmetry. So the tools they used were mostly geometric, but somehow what they do is easier to interpret in terms of the derived category than W itself. What do I mean? So first of all, the semi-infinite Hodge structures live on the space of formal Laurent series with coefficients in the de Rham cohomology of W. And this is known to be isomorphic to what people call the periodic cyclic homology. And the second thing is that they vary over what Baranikov and Kontsevich call the extended modular space of W. But that's nothing but the modular space of A-infinity deformations of this category. So it's kind of difficult to explain where these objects come from if you try to avoid the category. Okay, so now the natural questions are: how universal is this picture? Does the cyclic homology of any category carry, well, it better be functorial semi-infinite Hodge structure? This is just the first question. The next question, if we deform, if that's true, if we deform the category, is it true that we get a semi-infinite variation of Hodge structures? Next, if we start with some category of geometric origin, do we recover what we expect from geometry or physics or whatever? So I would like to talk about these two questions. If I have time, I may say something about the variations of semi-infinite Hodge structures, but it doesn't look plausible. So, any questions?
What's the structure of this extended moduli space? Because I'd always understood this as some sort of formal thickening of the classical.
Yeah, it's a formal super manifold. It's just a formal germ in the de Rham cohomology, the origin. It's just a space of formal series. The spectrum of this algebra of formal series on the de Rham cohomology of W. If you deform just W, then you see only a tiny part. In the case of three-folds, it's just H21, more or less. But to get a Frobenius manifold, you want to somehow include the entire de Rham cohomology. And there is no way to interpret this unless you employ these derived categories. Then so the Hochschild, you know that the deformations of an algebra or a category are encoded in the Hochschild cohomology. And so this Hochschild cohomology is kind of dual to the de Rham cohomology. So that's, yeah.
In one, is it supposed to be the same construction on the A and the B side?
Yeah, exactly, yes. So that's the main goal, because otherwise, yeah, this theory would be completely useless. We want to be able to extract some isomorphism of Hodge data from an equivalence of categories. So for that reason, we want this construction to be as much functorial as possible, but of course, it has limited functoriality, so it's functorial with respect to infinity equivalences between categories, not just functors. Okay, so it was some motivation. Now I would like to give the definition of a semi-infinite Hodge structure. Okay. So we start with a vector space, actually a Z-mod 2 graded vector space. Finite dimensional. Over the field of formal series in some variable u. It's just a formal even variable. Then weight W parity P semi-infinite Hodge structure on H is a triple where L nabla Q, where first L is CU lattice in H. So it's a full rank submodule, CU submodule in H. Nothing else. Nabla is a meromorphic even connection on H. Even means that it preserves this decomposition with just one property. This nabla has pole of order at most 2 with respect to this lattice L. So far these data do not depend on any letters W, P, and so on. Now Q is a pairing on H with values in this field having the following properties. First of all, it's sesquilinear. So I will denote this operation by an upper star. So lambda upper star of U is lambda minus U. The second property, it's skew symmetric. It's P skew symmetric, actually. Skew Hermitian, one should say. So this P is this P, and this star is this star. So you pair V2 and V1, you get a series, and you change the sign of the argument. Now it's nabla flat, but in the following generalized sense. That's where this number W entered the picture. And finally, of course, it should be non-trivial, and moreover, it should be non-degenerate in the following sense. Okay. So examples. So why should such a structure be called a Hodge structure? So of course we should be able to cook up something like this from a usual Hodge structure. So suppose H is a finite dimensional complex vector space that underlies some polarized Hodge structure of weight W. Weight W Q. Then this data gives rise to a semi-infinite Hodge structure of weight W and parity 0 on the space of Laurent series with coefficients in H. Namely, so L is simply the space of formal series, the submodule formal series. Now, nabla is given by the following formula where gamma, so we have some Hodge decomposition here, and gamma is simply the operator of multiplication by Q. And what else? Q, or this Q, is the unique CU ciscollinear extension of the form so these two vectors belong to H. V2, if V2 is in HPQ, then V2 check is -1 to the power P times V2. Okay, the second example. This example is precisely what you see in the picture of Baranikov and Kontsevich. So suppose W is a smooth projective so at this point it's not necessary for this W to be Calabi-Yau. Then you get a weight 0 of dimension n. Parity n mod 2, semi-infinite Hodge structure on this space. Namely, so L is again just the submodule of formal series. Nabla is given by a similar formula, but this time it's a multiplication by Q minus P over 2. And again, Q is the unique extension of the pairing given by this formula. So here V1 and V2 are some elements of this cohomology. V2, this check has the same meaning as over there, so you just take the wedge product and integrate. And finally, kind of the main example for me, and historically the first example of semi-infinite Hodge structures. So this is due to Kyoji Saito. So now I start, so let X be just a affine open subset in Cn, and f, a regular function on C, with isolated critical points. But I have to impose one more condition that may look a bit strange, but I will need it later. And so I will assume that this f has only one critical value. Value, and this value is 0. So if you have more critical values, then you should make your x smaller. Then let me set, so I will write out a semi-infinite Hodge structure on H given by the following formula. So this is what people call the twisted de Rham complex of F. So it's just a space, but actually in all these examples I should tell you what the Z mod 2 grading is. So in that example, it was the space was purely even. In the Baranikov-Kontsevich context, the grading was determined by the degree of the form, modulo 2. And here it's also purely even. Okay, so what is L now? L is the same thing with formal series here instead of Laurent formal series. Nabla comes from a connection on this complex. It's given by the formula d over du f divided by u squared. This operator descends to the cohomology. It commutes with this differential. And finally, Q is the higher residue pairing. So it's a remarkable pairing. I will not. It is defined through a collection of properties. There is not any explicit formula, except that it extends the usual residue pairing. So I denoted this by Q0. Where is it? Yeah, Q0 is the induced pairing on those quotients. So in this case, oh, sorry. So you take the sum over all critical points of f of the residues C So there is this pairing, but unfortunately it's very so how do I erase? Thanks. Okay. So this this is a weight n parity 0 semi-infinite Hodge structure. Now, I actually didn't include one axiom that some people add. Namely, they want nabla to have a regular singularity at 0. So, you may add it, or you may say that your semi-infinite Hodge structure is regular if this axiom is satisfied, but in all these examples, the connections have regular singularities at 0. In the first two cases, it's quite obvious because we simply have a logarithmic pole, but it's also true here.
It is called the Calabi-Yau property?
No. Okay, so now the main subject of my talk. So, for simplicity, I will start with the DG algebra. So let A be a Z-mod 2 graded differential algebra. So what it means? It means that A is a complex and at the same time a unit-O associative algebra, and these two structures are compatible. So the multiplication preserves the grading, and the multiplication satisfies the Leibniz rule with respect to this differential. So my goal is to define an semi-infinite Hodge structure on what people call the periodic cyclic homology of A. Okay, so let's start. First of all, what is this? It's the cohomology of a complex of this complex. What is what here? C star A, it's the direct sum over L of tensor products of the following type. So what is A red? A reduced. You simply quotient out the subspace spanned by the unit of A. So this is actually what people call a normalized Hochschild complex. P is the reversal of the Z-mod 2 grading. What was even becomes odd and vice versa. So that's the underlying Z-mod 2 graded vector space. Now this D, the D is simply so once again, D underlined is the total differential. So A comes with the differential, and so this tensor product is also a complex. So D underlined is just the differential in this complex. B is the Hochschild differential. So it's of the following shape. You take the sum over various pairwise products, A0, A1, tensor A2, and so on. Then A0, tensor A1, A2, and so on. And in the end, you move the last term to the front and multiply with A0. And B is what some people call Kahn's differential. You put the unit in front of everything and then take the sum over all cyclic permutations of these letters. Okay, so that's the space that should carry some semi-infinite Hodge structure. What are the candidates for L, nabla, and Q? So L is the same thing with, again, with just formal series. This is what people call the negative cyclic homology. Now, there is an explicit nabla. So its existence was, say, observed some years ago by Kontsevich and his collaborators, but they didn't give an explicit formula, but the formula turns out to be quite simple. So let me define two operators on this direct sum. Gamma prime, it takes this tensor and does the following thing. You apply the differential to A1 and then you multiply these two things. The first two, L. Gamma double prime, it's a bit more complicated. It's 1/2. 1/2 I, the sum over I and j, I less than j, it's 1 d a j a l a0 And also you have to subtract a sort of a grading operator. Yeah, sorry. Of course, it's just. Sorry, Kerry, one second. I'm trying to correct my formula. Yeah.
Going back to the discrete homology group, the co-boundary operator just has 3 terms, D, B, and UB. Can I give more in geometric which correspond to which geometry? In my case, I have 2 terms here.
Yeah.
Differential D and U times D.
So this sum is roughly the wedge product with df. And this is the derived differential. Okay, then it turns out that this operator descends to the cohomology. So all these operators, in principle, are defined only on on the complex, but if you take this combination, it descends to an operator on the cohomology, on the periodic cyclic homology. Okay, what else? So this pairing Q. So there exists a pairing such that it's defined as a composition. Sorry, forgot an important thing. Of course, a pairing has a chance to exist only under some properties assumptions on your algebra. It cannot be some algebra of polynomials. So I should assume here that A is proper. That means that its cohomology is finite dimensional. And so this pairing is defined as a composition of several maps. Okay, let me skip this pair. It takes too much time. So this AOP stands for the opposite DG algebra. You just reverse the order of multipliers when you take the product. And it turns out that there is a canonical isomorphism between these two spaces, but this isomorphism is anti-linear. So if you multiply some element by lambda u, here lambda of minus u pops up. So this is the first map. It's just the identity on the first part and this canonical isomorphism here. This map is a noncommutative QNet map. It's a well-known map in noncommutative geometry. Now, this map from here to here comes, so this end A is simply the algebra of endomorphisms of A viewed as a vector space, as a complex. And so you have a homomorphism from this algebra in here, given simply by the left and the right multiplication on A. And this periodic cyclic homology is functorial, so any homomorphism gives rise to a map. But this thing is simply isomorphic to the field of Laurent series. It's due to Morita equivalence of what people call DG Morita equivalence of periodic cyclic homology. Okay, so you have this pairing, and now I would be happy to tell you that this triple is a semi-infinite Hodge structure, but that's not true in general, unfortunately. And so this. For a variety of reasons. First of all, the periodic cyclic homology doesn't have to be a finite dimensional space. Well, your algebra has to be really exotic for this space to be infinite dimensional, but in principle it's possible. Now, this negative cyclic homology may have torsion. The form Q may be degenerate. Even if it's not, it doesn't have to be skew Hermitian in general. But nevertheless, we have this theorem. So A as before. DG algebra. Assume, in addition, A is smooth, or the original term is homologically smooth. It means that A is a perfect A bimodule. Assume that this negative cyclic homology has no torsion. Well, in principle, people expect this condition to follow from this condition. That's a well-known Kontsevich-Sobelman non-commutative Hodge to derived degeneration conjecture. It was proven by Kaledin a couple of years ago, but not only in the Z-graded case. Now, assume that A is a Calabi-Yau DG algebra of dimension n. What that means is that you can take a dual vector space to A, it's a bimodule, and this bimodule should be quasi-isomorphic to the nth shift of A. That's a precise non-commutative analog of the triviality of the canonical bundle. Then the above triple is a semi-infinite Hodge structure of weight 0, parity n, where n is this n. Okay. So under this condition, the pairing is non-degenerate. So we have taken care of this problem. Under this condition is the pairing is skew-Hermitian. It's not my result. I conjectured this in one of my papers, and in 2015, Nick Sheridan showed it. And so we have this result.
The assumption that A is Calabi-Yau, is it the same as the existence of self-functor?
Well, A is not a triangulated category, so it's under this condition. If you consider the category of modules over A, then you get a category of perfect modules over A, then the derived category has a self-functor, and the self-functor is just a shift. Okay, so I have 3 minutes. I promised to say something about this case. So I cannot give definitions anymore, but you probably know that to any function as above, people associate categories of matrix factorization. So xf gives rise to a DG category of matrix factorizations of f. This whole story extends to differential graded categories, but of course the formulas are simply longer. Okay, it has all the nice properties. It's smooth, it's compact. It is a Calabi-Yau of dimension n, where n is the number of variables, modulo 2. So it would be interesting to compare the non-commutative Hodge structures that you get from this category with what we had previously from geometry, the twisted de Rham complexes and so on. Why is it a reasonable question to ask? Because this category describes the boundary conditions in yet another topological string model. It's what physicists call Landau-Ginzburg B-model. And Saito's theory turns out to describe the closed sector in this theory. It was explained by Bloch and Varchenko in the early 90s. So it's the same philosophy. We have a topological string model, a category, a closed space. How do they compare? Well, definitely they cannot be isomorphic because you see, here we don't have any shift, so our non-commutative Hodge structures are always of weight 0, no matter what we do. But in the geometric case, the weight is n, the number of variables the function depends on. And so they are not isomorphic, but are quite close. It's what we had before. Let me denote this by LF. So it's a twisted de Rham complex. That's the connection we had before, and this is the higher residue pairing. So we have to tensor with an analog of the Tate structure. sorry. So it's a one-dimensional weight n minus n, sorry, minus n parity n mod 2 Hodge structure living on just even or odd copy of C. The connection in this case is d over du minus n over, sorry, let me make sure that I'm not making any mistake. To u. And q in this case is just, so everything is one-dimensional. You simply reverse the sign of the argument and lambda 2 and multiply. So the proof is quite technical, but it also depends on a very nice result of Marihika-Saeta. So there is a map. I mean, it's hard to prove it because neither this pairing nor this one are explicit. I mean, how can you compare something that you cannot define by a formula? But there is a result of Marihika-Saeta saying that the high residue pairing is the unique pairing flat under some extended Gauss-Manin connections, fully extended. It's just the only property that determines this pairing up to a constant. And so I had to deform both sides to show that I have an isomorphism of some semi-infinite Hodge structures, variations of Hodge structures. And then the result follows. Okay, I'll stop here.